There is really no difference in temperature of the cell at really fast charging. We realize that we're now sitting at about 5 to 6 times better energy density with our graphene over any other graphene we've tested in the world. We're only using one of the 3 electrons so far. See, aluminium has 3 electrons, lithium has one, manganese has two. We have 3 electrons and we're only using one of them so far. Now we are working on the ability to use all three. And arguably that would be 3 times where we're at now in terms of energy density. So we started working on multi-layer cathode design, and we've been able to make a number of multi-layer cathodes, which is obviously the next step for pouch. We've been able to make multi-layer coin cells and also multi-layer pouches. So that's the next step.
Well, I'm excited to welcome back the founder and CEO of the Graphene Manufacturing Group, Craig Nicol. Welcome back to Cleanerwatt, Craig.
Yeah, thanks for having me back on, John. Really appreciate it.
Definitely. Well, I know this is a topic that I'm definitely interested in, graphene aluminum-ion batteries, and my audience has been very interested in this topic as well, based on how many people have watched those videos. But I do recommend, if you have not yet watched the last interview that I did with Craig, we recorded that in late July of this year. So it's still pretty up to date, but we're going to provide some new updates, some exciting updates on top of that. But if you have not yet watched that previous video, I will link to that in the video description. I recommend you watch that. I don't want to repeat a bunch of that information. That was like a 40-minute interview. I don't want to spend too much time there, but Craig, just in case there is somebody listening right now and they have not yet watched that video, can you just give us like a 1 to 2 minute brief introduction into the company Graphene Manufacturing Group and maybe how aluminum-ion battery technology fits in as well?
So Graphene Manufacturing Group is a 6-year-old Australian public company. We listed on the Toronto Stock Exchange of Ventures. We have 3 main technologies. One is to make graphene from natural gas. That graphene then we make for ourselves. We no longer produce that and sell that for anyone else. We then put that into, so for a start, nobody else really does that, especially in a public market space, in a continuous type plasma. And so that graphene is very unique, and our proprietary way of making that graphene is very unique as well. Then we then can put that into a second type of technology, is where we put that into a fluid, and then we sell that product. So whether it's a lubricant concentrate to top up onto existing lubricants, or it's our thermal XR, which is air conditioning coating. So that's our second type of technology, where we provide a support, a fluid-based dispersion and distribution for our graphene. And then the third type of technology is what most people want to talk to us about, which is our Graphene Aluminium-Ion battery. That technology was developed by University of Queensland. It was announced a year and a half ago. They have been able to top the next best in this aluminium-ion technology, which was Stanford. They did about 4 times better than where Stanford got to with our graphene in terms of energy density. But it's also extremely fast charging, about 60 to 70 times faster charging than lithium-ion batteries, and has many other benefits. So we took that as a license, global exclusive license from University of Queensland. And in the last year and a half, we've been engaging in the transfer of IP from that. And then, obviously in the last couple of months, we've come out and announced an upgrade of those energy densities and also power densities. So I think that about brings it up to speed, John.
Perfect. And before we dive into the really exciting, really meat of this conversation and the update with the gravimetric and volumetric energy density increases, and also the power density increases, before we dive into that, I have a couple questions, really 3 questions, which are follow-up questions from that past interview. Several commenters had some questions, including the first one. One commenter wanted to know about information about the nominal operating temperatures of these battery cells during fast charging and discharging. This really has to do with the fact that we had talked about how graphene and aluminum, they have very great heat dissipation qualities. So what kind of nominal operating temperatures are you looking at for your test cells when you're doing those discharge and charging cycles?
Yeah, so we've done some, I'd suggest, lay testing. We're about to go into professional testing of this. We have all the test kits for temperatures for below zero and up to 100 degrees being literally set up for the batteries now. So we can come out shortly and with real conclusive data. But so far, the testing that we've done has shown there is really no difference in temperature of the cell at really fast charging. And that makes sense. So, the nominal temperature is basically the room temperature that you're charging it at. Even if it's charged at, 100 times temperature, 100 times amps. That makes sense because our graphene is used to dissipate heat in another product we have, and it's exactly the same graphene, except slightly different nano flakes that we use. So I'd suggest to you that there should be no issue even at further or higher charging rates in the future because of its ability to dissipate heat, which we're otherwise studying in a range of different technical pieces of work. So we feel quite confident that the heat management side of our battery is going to be well taken care of by the internal graphene. So I think that should answer that question.
Very cool. And kind of a follow-up, it's somewhat related, but not just during charging and discharging, but what about, throw these batteries in a product that is in sub-zero temperatures, like freezing, below freezing, and maybe even more extreme than that. And then also take these batteries and throw them in a high desert environment where it's really hot. How well do they operate in extreme temperatures?
Yeah, so I think we've tested to 0 degrees, so freezing, but we didn't see any difference in temperature. What we've got to watch for is the electrolyte and what does the electrolyte do. And so sub-zero temperatures, I think, will be okay, but we've got to work out when. At some point, it will not work as best that it was at ambient. So far, we've done some interesting things with different types of early testing on heat. I think we've tested it to 80 degrees Celsius with no difference in performance. But as I said, we have yet to actually fully test it in our temperature chambers, which we've just set up. So I think that'll have a lot more conclusive data, but because you actually got to charge and discharge inside that temperature. So it doesn't need specific equipment, as I said, that we have now. So we'll get more data and be able to announce that when we have it. But for all intents and purposes, I think they'll be very good in the desert. And I think they'll be in very hot places. I think that it's going to work out how cold they can go. I think our battery would be great for space. It would really be able to take whatever comes at it, because obviously it's a pretty harsh environment in space. And we've been somewhat talking to different universities around that opportunity. But yeah, I think in terms of both ambient and then the heat that comes from the charging and discharging, I think that will be not our concern going forward.
That's good to hear, both for me and also the person that asked that. I think it's a great initial bit of information. I'm definitely excited to see the follow-up with your more robust test on that, but I appreciate you answering that. Really, the last follow-up question before we dive into the announcement comes down to really, what are some limiting factors to this technology? We kind of briefly talked about this in the past interview, but basically the question is, if these batteries are so great, aluminum-ion batteries are so great, why don't we have them as one of the predominant technologies in batteries right now?
Yeah, and it just comes down to graphene. I mean, the chemistry is known. The fundamental difference between even where we were last year and now is our graphene. That's all it is. It's having the structure so that you can bring the aluminium-ion in and out. That's all that this battery is about. Mass production of the right quality of graphene. If you just imagine all the graphenes in the world are all the different types of oils. And so, yeah, you can have an engine oil, you can have gear oil, hydraulic oil, but there's really only one oil that works and we've found the right oil that works for our battery, and now we're optimizing that. So there are many different types of graphenes, and you need to find that graphene and then optimize it for what we're doing, and that's what we've done. And now, we've obviously got to scale our production in line with our battery demand, which is, if I was to say what it is, it's enormous. So that will be largely our controlling factor.
Obviously the Graphene Manufacturing Group, you have a good advantage there since you're manufacturing it yourself. You can get it to the exact specification that you want, et cetera. So that's key.
It would be almost impossible to do this if we weren't making our own graphene. That's clear. You need to have one team making the graphene and one team making the battery, and they talk. And then sometimes I split them apart. Says, go do your thing, and then we'll meet up again, and then we meet up, and then we shared notes. That's the only reason why we have what we have. There is no other way that this battery could have happened. I look at that now. And actually, for a while, we did have some other graphenes that were better than ours, and then we found that secret that we're looking for in our graphene production, and realized that we're now sitting at about 5 to 6 times better energy density with our graphene over any other graphene we've tested in the world, and it's repeatable. So that is the crux of our progress, this year, as a company, to be able to have that definition and repeatability of and to know what you're looking for. And it's never what you want. In graphene, we've been doing this for 6 years now. It is never what you think it's going to be. You think you're defining this, and you get there, and you've got to define that, because it's a very obtuse product. It's literally a quantum product. So you really do need to do it through enormous amount of trial and error. And that's what we've come out the other side for. So yes, graphene production is the controlling factor and limiting factor going forward. And we think we've cracked it. We've got to do more work, but we feel a whole lot more positive around being able to take this to market. And that's why we're planning now timelines for battery production.
Now let's move to really what we kind of talked about earlier, what I hinted at earlier. But when we last spoke, you talked about how the gravimetric energy density of your test battery cells was somewhere around 150 to 160 watt hours per kilogram, which was already incredible for aluminum-ion batteries. But the recent announcement, you have now increased that by 93% to around 290 to 310 watt hours per kilogram. So within that, what changed, and how were you able to achieve such massive increases in energy density?
The two main ways that we've done here is increase our voltage. So when we came out last time, it was 1.7 volts. Now we're sitting at 2 volts nominal. And that's a big thing. To shift to 2 volts nominal is obviously a pretty big increase right across your energy, because that's just a straight multiplier. And we found a very interesting way of how to manage our batteries that allows us to achieve that through an enormous amount of work. We found a way to lift the voltage, which is just a plus right across the board. Now, the second way we were able to increase our capacity was, or our energy, is just through increasing the capacity per gram of graphene. And that's just being able to fit more ions into the graphene. That's all that is. So when the atoms come across, or ions come across, if you can fit more of them per gram, that means you increase your energy density. So that was, there was an enormous amount of work to do that. Now, the third way of increasing energy density is removing weight. And that's obviously just by removing the non-active material weight. And that's something that we can optimize on, but right now we're working on. But just with respect to the second one, in terms of increasing capacity, there's actually a fair number of things that I can go through if you like that we've actually done. If you want me to go through them.
Yeah, within that, I want you to go through that, and also as a follow-up, as you move into that topic of the technical aspects, does it have anything to do with harnessing more of the available electrons of aluminum? That was something that you had brought up, and if you can talk about that topic within that.
We're only using one of the 3 electrons so far. See, aluminium has 3 electrons, lithium has 1, manganese has 2. We have 3 electrons, and we're only using one of them so far. Now, we are working on the ability to use all 3, and that's just in the electrolyte. And so we're working on a next-gen electrolyte already, which is very encouraging, and arguably that will be 3 times where we're at now in terms of energy density. Now, there's a range of things I can go through in terms of what we've done to bring the capacity up. First of all, we've optimized the substrate material. Now that's the material that the graphene actually sits on, the cathode substrate, and its preparation. There's probably about 15 steps, and each one of those steps is just absolutely crucial that it's done the right way. But what is the right way when nobody's done it before, so to speak, at scale? So that is definitely important, and how the material is even prepared. It's really interesting. Even how it's cut or how it's managed is very important as well. And it's counterintuitive, and it's not the same as how lithium is necessary. Lithium cells are definitely made. And then we've got now a repeatable ink cathode. So what we take is the graphene 5% binder, generally 5% some type of solvent. Currently, what we're working on is using just water. So it's graphene, water, and some small binder. So we're trying to move away from the PTFE. We're trying to move away and to a natural binder. I think we're using a natural binder generally. So that's generally in a lithium battery. You have NMP solvent, and generally you have PTFE binder. So we're trying to move away from those. It's very natural products otherwise. So it's just our graphene made from natural gas with hydrogen byproduct, and then 2 small additives for the ink. Then that whole mixing fluid, that whole process that we use to make that into the final cathode is definitely very important. We found some very unique opportunities there. Now, the next thing is what loading are we working on for the cathode? And they're all different methods, and there's not one single method that's right. There are many ways to build a cathode. Now, generally you sit at high, medium, and low. And high is generally where lithium sits at. Lithium sits it with a big load of cathode thickness, a whole lot of carbon effectively, anode for that, for lithium. And then that has all sorts of advantages. It enables more spaces for the ions to sit, but then the thicker you have, the ions have got to travel through the matrix of the carbon to be able to find a place to stay while the electrons going around. So you have trade-offs there, and everything in the battery is a trade-off from one to another. And then there's medium, so that might be 50 microns high, and then there's medium, say, or maybe even up to 100 microns, and then there's medium, say 20, 30 microns, and then it's low, kind of very small, 5 to 10 microns. And so we've tested all of those. Right now, we're very favorable in low, but we can also do medium and high, but we are actually favoring the low cathode thickness. The electrolyte corrosion was always seen as a problem for this battery. And if you look, even Wikipedia would say this type of battery has electrolyte corrosion issues. Well, we've fixed that, but then we've also fixed the internal resistance as well. So there's a major 2 steps which actually help us to be a whole lot more repeatable on this and as well on making the batteries. Now, the electrolyte is really important. It's the most unstable of all our batteries, even though it's an aluminium salt is the reason why we get it. Yeah, and we've pretty much fixed that as well, and that took a lot of work to be able to work out how much of the electrolyte do we put in compared to, and how do we make that repeatedly. And that is it's a major step forward. We blew apart a lot of paradigms to get there, and I think the team's done a fantastic job in testing all sorts of different ways that can be run. Basically the more ions you have in the electrolyte, or the more atoms, the more viscous it is, and the less it's able to permeate. And the less ions you have, the less viscous it is. So that means it can permeate the cathode more. So there's a trade-off of how much how active you actually make it, and then how corrosive it is, the more active it is. So we've been able to manage all those through as well. Now, with a single layer, with a thin layer, you've got to know, you really got to be able to start working on a multi-layer. So we started working on multi-layer cathode design, and we've been able to make a number of multi-layer cathodes, which is obviously the next step for pouch. We've been able to make multi-layer coin cells and also multi-layer pouches. So that's the next step. What's the next stage for G&G? Well, it's getting into semi-automated and automated, because manual making of cathodes and of multi-layer cathodes is almost impossible. We genuinely, a lithium battery won't get more than, say, 20 layers of a cathode in one battery. Because ours is so thin, we're expecting anywhere up to 50 layers. And to put 50 layers in, I think you can imagine doing that by hand in a very small kind of cathode, as in winding or Z stacking. So we'll keep working on that, and that's obviously the next step we're going to as we progress into a multi-layer cathode, which will really push our whole product development along as well. So there's more things than that, but that's a good list of all the things that we've been working on to kind of really optimize our battery and get where it is now, which is quite a repeatable battery, a repeatable process with repeatable graphene.
So as I understand it, the higher the voltage, generally the higher the corrosion of the electrodes and the shorter the life of the battery. That's how I understand it. So yes. I assume that's a huge advantage to your current technology. You're operating at a very low voltage. Is there a downside to increasing voltage when it comes to your battery life cycle? Like, do you really want to stick to that 2, or do you really want to go to 3 and above? Can you talk about that?
There's certainly ways to push it, and we haven't done them repeatedly, so we can't actually talk about them, but there are ways of it to be able to, increase the voltage. We're certainly very happy with 1.7 to 2 volts, because you double that and you're sitting with a lithium pack. And in a pouch pack, it doesn't really matter what the voltage is. Because if you want, say, 10 volts, or you put in 5 of ours, or you put in, 2.5, 3 volts, 3 times for lithium. So it's really not an issue, apart from if you're really making a definable cell that is exactly the same shape as another battery, which is typically, say, a coin cell. And that is always going to be the problem with a coin cell for us. And we've been able to work around that, and we're working on it. We're just doubling up the battery to get you the 4 volts. But yeah, I think something we have noticed is if you push the voltage too high, it can reduce its life. So well above the 2 volts. If we try to get a nominal voltage above 2 right now, I think it does reduce the battery life. It starts to deplate the anode, the aluminium foil, and starts to go a bit wonky. So yeah, that's something we've got to watch. But the ability to jump up to, say, a 3 volt would probably just be based on the fact that we're using 3 electrons, not necessarily really doing much more with anything else, right? So I think there's opportunity to get it up to 3 volts, potentially, and then sit at just the same corrosive level resistance we have right now, which is basically very good corrosion resistance. I don't think we've had a cell corrode for months because we solved that problem separately. And there's a lot to say to making 100 coin cells a week, so to speak, that enables you to be able to say what works, what doesn't. And that's the thing you've got to get to is you've got to have a bit of a bell curve of where does each product fit. And that's the thing we'll be working into next is we have a very good idea of where it sits average wise, but okay, let's look at what's the percentage of variance outside that average. And that's the data we need to have at really quite really quite depth and at various different optimizations. And once we're there, I think we'll then have a much better idea of the real ability to push one lever and get a problem somewhere else in the minutest level. Though right now we're looking at failures, modes, and things falling off significantly. We'll start to optimize on small changes, small outcomes, and then we'll go further into the matrix like that, which is obviously what people expect of a battery, especially a high-performance battery. And that's, as I said, that's the space where we need semi-automatic machines, automatic machines, and that's what we're working on now. And we're putting together, and then just increasing our team to be able to do that as well.
Okay, that really actually moves perfectly into the next topic. So I appreciate you giving some technical details on that energy density increase and that information. I actually want to move into your pilot coin cell facility. If you can give an update on how that's coming along, how that's going, like what you were producing there. Are you still, as of today, producing cells by hand? And what is the progress with the automation equipment? If it's not starting to be used now, when do you think it will be?
Yeah, so there's two batteries that we're looking at working on. One is the coin cell 2032, 1,000 cycles rechargeable. So in effect, you can use it over and over again, which enables you to stop buying the lithium ones, which are actually causing an environmental stockpile in most countries around the world. And then the second one is a pouch cell, which is really kind of B2B, be pushed out to various different types of big companies that kind of want to swap out from the lithium. The coin cell and the pouch cell are both still manual. That is because we're still making sure that every step is optimized to where we need it to be. The next step for the coin cell is to go to an automatic production system. It's semi-automatic coin cell production systems aren't really worth that next step. It's once you've actually made a good coin cell, you can pretty much go to automatic production. So we're scoping that out with Bosch already. We've had a number of couple of days where we work with them, and it's been extremely good workshop. And they've really come in and shown what's possible with existing automation and existing battery systems, which we kind of knew as well, but we kind of brought them together. And so now we're scoping that out, which we hope to take a final investment decision on sometime next year, and then hope to be in production in 2024. That we think that'll be in the order of millions, but we don't obviously haven't finalized that, but that'll be order of millions per annum coin cells. And then you'd have to have a recharger, which would come with that, like a little USB charger. Now, the pouch cell is different. Pouch cell, you actually need to have an automated type assembly process to be able to get it exact. And when you're winding 20 layers of it into a pouch cell, you really want to do that just the right way every time. And manually, it's quite difficult to do, almost impossible. So semi-automatic pouch cell plant is what we're looking at right now to procure. We're kind of bringing that together. And I think that will really enable us to step into a lot of really close development with some big companies that we're talking to. And then they can test our pouch cells. We might have thousands a week or so out of the system. And then they can test our pouch cell and see that we have the right dimensions for the battery that we're after, and then go from there. So that's really quite exciting. But that's still to be worked through, and that could well be later if we have a much bigger plant by design.
Okay, so if I'm hearing you correctly, you hope to be maybe selling some of your first coin cells in 2024-ish, and sometime around 2025, maybe you are sending samples of your pouch cells. Maybe pouch cell samples are being sent out in 2025 for
pouch cells
potential
could
testing.
Well be even. Yeah, I think pouch cells could even be. I mean, we can send it out now, but not too many. I think pouch cells we'd like to send them out next year. But then 2025 we could be looking to do a large scale plant. That's kind of a construct there.
Any licensing plays here? So obviously you're talking about manufacturing a lot of this yourself, but is there any room there for you to license your technology, and at the same time you'd sell them the graphene they need, etc.? But do you plan to license this out to anyone?
I think the licensing really only does come up once you've got a plant operating. People who license it really need to take a bet, much bigger bet before you've done that. So we'll get up our plant, and our board hasn't made a final decision whether we'll license or not. But I'd suggest to you that if we did have it operating and everything was working really well, and someone said, "Look, I will scrub out my lithium factory," which is all they need to do. You build a graphene plant next door with from a gas pipeline, and I will just convert my whole lithium factory over to Aluminium-ion factory. We'd probably take a very good look at it, because that's all that's needed. It's basically the same equipment, and less, because on our anode we don't have any coating, so it's actually less equipment but the same equipment.
Very good. Okay, so I appreciate all that. I want to close this conversation and talk about graphene manufacturing itself. So we talked about the process last time. I'm not necessarily asking you about the process, but I want to know more about how much are you actually able to manufacture right now for your own use? I think you mentioned earlier you're not selling it now; you're using it yourself for your own products. And then within that, you have your HVAC coating product and your lubricants with your graphene in it. Can you tell me, roughly how much of this product are you actually selling per year? How does Graphene Manufacturing Group make money today, and what kind of volumes are you doing now, and what does that look like in the future? I think this is important for potential investors to have this kind of information.
Sure. So we have no formal guidance out. We're obviously maturing through 3 different markets. But I can talk you roughly through how we are moving through our commercialization and what I call our maturation of our company. So Thermal XR is the most developed in the market in terms of number of salespeople we have. That product is well and truly able to be sold. We have the rights, own the rights, and then we also have the legal approvals to make and sell that to the Australian government. So we have a number of projects around the world that are progressing well, and we have a number of distributors around the world that are progressing well to be able to effectively sell that through the HVAC or air conditioning distribution networks in those countries, and that's progressing well. We've certainly sold some, but the notable revenue that we're obviously seeking is still to be coming. We believe that notable revenue is not far off. You've got to have an enormous amount of data to be able to show people why our coating can shift heat faster than if it wasn't there in the first place. That's not initially intuitive to people. They've almost been taught at different parts of education process that's not possible. So we're doing things that have kind of gone against what people would normally think, and you need lots of data and lots of testing, and each country kind of needs their own testing. right? So we test it in Australia, and they go, well, I want to test it in America. Okay, so we'll test it in America. And then Asia, different parts of Asia will want their tests done in their places. So, and then Middle East is the same as well. So there's that we need to go through. So we need to build what we call the reasons to believe, the RTVs, and let's build them with data that in their country, and make sure we have all the right approvals. So that's where we are with that. And I wholeheartedly believe that our thermal XR will be a product that will be widely used in the air conditioning sector, as well as big power users. So we've had a number of projects there in different energy producers, including liquefied natural gas. And because it's the same process, right? You're trying to cool and make things cooler faster. Now that's a product that we will soon be making completely ourselves. We're building our own plant to be able to blend that. And previously we've been buying it from the person who developed it, the company who developed it, but we've done that deal to take that over. So that will then also mean we can optimize how we use it, where we use it, where we sell it, and we have all the rights to be able to say everything about that product. But previously, we didn't have that complete right because it was owned by somebody else. But that's changed a couple of months ago. Now, in terms of lubricant, that is just our graphene, our blending process. It's a concentrate. It is dropped into pretty much any oil that you have out there in terms of engine oils. We have deep lubricants knowledge. I was the marketing manager for Shell, Oceania industry sector, myself. So, and there's a number of other people in the group who have oil knowledge. So there's in this is something that it's even more difficult to get people to, I guess, convince themselves on, because snake oil salespeople are literally the the definition of saying something which is not true. And I wouldn't have it in the portfolio if it wasn't a good product. We've tested hundreds of applications, and we know there is something really good there. And we've been working with a number of big companies on getting up a first trial. And that we have already got some exports to Asia up and running, a commercial scale production. They're small orders, but they are a step in the right direction. Obviously, the battery is very different. We actually don't market our product. We've never actually gone and sought a customer out. They keep seeking us, and that continues to happen. And as I said, hopefully we can try to get into some type of revenue situation with our pouch cells next year in terms of R&D and sending out pouch cells. And then hopefully we can push into some coin cell revenue in 2024.
Okay. And so you think the thermal XR and the oil lubricants, you'll start seeing revenue. I sounds like you may be making a small amount of revenue from those products now, but basically when will that revenue pick up for those products?
Look, as I said, we don't have formal guidance, but I think 2024 we should have some notable revenue around that time. But we will. 2023. I meant to say. All these years are a bit difficult. They go by faster and faster. But 2023, I think, is when we should see some notable revenue, and that's what we're really pushing for.
Perfect. Because that was actually something somebody had brought up in the last conversation, things like that. So I think that's an important topic. Once again, it's not as important for the technology that we were talking about here, but it's important for the company to exist. The Graphene Manufacturing Group has to make money for it to exist. For these technologies, for this Graphene Aluminum-Ion battery to ever be mass produced, you have to be a profitable company. You have to be making money. Investors have to believe in you, at least at the beginning, before you get to that level of profitability. But at some point, a company has to be profitable. So it's good to know that you're on that path.
Yeah, and I think that's a real benefit of GMG is that we have two other products. We have other products we could make with that graphene. And that's probably very different to other battery companies, is that we have the opportunity for good cash cows already available, already be able to be produced, and good margins, very high margins, and world-leading products. They're both with our parallel in the market as well.
Very good. Last question, and then I'll have you close. What does the GMG team look like? Number of people, like how big is the GMG team? Your sales team, the people working on manufacturing. How big is that team right now?
We're about 45 people. So we've substantially increased over the last few months. And we're basically largely based here in Brisbane, Australia. So we have generally around 10 people making the graphene every day in automated factories. We've got roughly 10 people selling, marketing, and about 10 people making the batteries. And then there's people like me in the corporate space with directors around the world. So we're going to continue to grow. We'll continue to put on people, but we'll put on people responsibly in a prudent way. It's a pretty crazy world out there right now. So you've got to watch, not grow too fast, not grow too slow, and grow at the right speed, and then really shift as the market shows that we're getting where we need to be. So it's a demand-led growth strategy that we're focused on.
Perfect. Cool. Well, thank you so much, Craig, for all that. Great updates. And I like that you dove into a lot of the technical aspects, which I think my audience will enjoy. If you just want to close us with any last words that you want to leave my audience with.
Yeah, I think just keep up the support. It's important to kind of give this technology the right support. Just look at the amount of opportunity, but then there is a lot of grandfathering that happens with an existing chemistry. And so the support is really important. As one very large battery buying company said, don't produce a battery so fast that you stuff it up, but don't produce the battery so slow that you miss the market. So it's not only got to be done right, but it's got to be done at the right time, the right pace. And the support is very helpful. So thank you.
If you work in the automotive sector and you want to reach out to me, feel free to email me. My email address is John, Jon, at cleanerwatt.com. Again, John, Jon, at cleanerwatt.com. And also, I'd like to take a moment to thank the Patreon supporters who support me every month and help make this content possible. A special thank you to my performance supporters and also the other supporters listed on the screen. If you'd like to find out more about the Patreon community I've set up, I'll put a link in the video description. Thank you so much.